Good evening, everyone. I'm very honored to kick off this year's Moldova DevCon. I'm especially excited to be in Moldova for the first time in my life because of this conference. And as a first-time traveler to Moldova, I'm looking to not only attend this conference, but also explore some of the things that Chisinau has to offer while I'm here, that I could maybe do before and after the conference. So how may I go about finding some things to do I might enjoy while I'm here? Well, I could pick up a good old travel guide, but it's the year 2025, so probably my quest involves some kind of search technology. And apparently the clicker is also very excited to be here. Let me check that. Yeah. Give me a moment, please. Now, in this talk, I want to take you through some of the approaches we can use to solve this problem. And I'm going to walk you through some of the search techniques that we may be able to apply, from simple string matching all the way to modern AI search techniques to turn this problem into a delightful search experience for our users. Okay. So let me first show you the demo application that I developed for this talk. It's a simple web application called Things to Do in Moldova. And below the headline, you see 6 different buttons that each take me to a different type of search technique to search around for different things to do in Moldova. Let me start with the first, simplest one, which I called the string matching approach. So this takes us some of the way. I can type in something like museum, and I get back a list of museums in Chisinau, for instance, the National Museum of History, that I can go and visit. And this type of approach is really simple to implement, and in fact can be done with probably my existing tech stack, such as a relational database engine. So you may put in a SQL query like the following, and it's really nice and easy and fast and easy to implement. But unfortunately, this approach takes us only some of the way. So it breaks down quite quickly for things where the user doesn't put in something that we have in our data set, but maybe includes a typo, which I would really like to show you. Here we go. So let's say a museum is spelled wrong. Now we cannot return any results to a user. Let's say the user puts in something like cafe, but misses the E on the accent. We cannot return anything because this cafe is not returned, included in our data set. But if the user searches for something correct, then we can show something. So what we're missing here is a possibility to do what's called fuzzy search. So to search for something that is very close to what the user put in, but maybe not exactly. What we're also missing here is a notion of relevance. So we don't only want to throw results at our users, but we want to return the things that are most relevant in the very top so that they're quickly finding what they're looking for. And lastly, it's also lacking performance, because what we're basically asking our database to do here is for every user query, iterate through all of the data in our database and compare all of the strings with each other, which is very imperformant at scale, especially when looking at high volume of user requests or a high data volume. So how do we solve for this? This is why full-text search was introduced or invented. We can do all of the things we couldn't do before, like look for things with typo in the name. We can look for things like cafe without the accent on the E, and much more than that. So we have this fuzzy search capability. We also have the notion of relevance here. So as you see in the result set, actually the results that are on the very top have the word cafe not only in the title, but also description and the category fields, while the ones that are further down below maybe only have cafe in two or one of those fields. And we can really tweak this relevance. We can make it personal to our users, so we can basically re-rank the results based on what the user has done before on our site, and so on and so forth. Modern full-text search engines are also highly performant at scale. So we can throw high amount of user queries and data at it, and it still performs at a very high level so that our users get results very quickly. We have additional things here like highlighting, where we can show the user not only the results, but also why those results were included. We have an entire field of text analysis, where we can say history and historical should actually be treated the same, and introduce, for instance, synonyms so that coffee and cafe are treated the same. There are other nice-to-have features for certain use cases, like did you mean and geo-proximity search, which would be super cool to implement for this, if I want to include only results that are very close to me currently. And all of these things are included in modern full-text search engines. Now, there's a lot more to talk about, and we could talk about full-text search all day and all the features that we can get from that. But to really summarize, modern full-text search is really something that our users are expecting from us. It's not going to blow them off their feet if we don't put a lot of effort in it and really fine-tune it, but it's going to keep them happy. And in fact, many customers that I talk to that want to implement full-text search, where they're currently doing something like the string matching approach, are thinking about it mostly because their users are actively complaining about the limitations of the other approach. So let's have a look at why a modern full-text search engine can perform all of these things and give all of these features that we discussed before. And it really boils down to a data structure called the inverted index. So in full-text search engines, we don't only store all of the documents in our database, but we also index them in this inverted index. And an inverted index is basically a map where the key of the map is a word or a token, and the value of the map is a list of documents that contain this token. So you can imagine if a user now comes and searches for cafe, all that the search engine has to do is look up this cafe token in its map and very easily get a list of documents that contain this token. So this can be very performant compared to the previous approach where we had to iterate through all of the items in our data set. We built this inverted index for all of the fields in our document, so we can search across different fields by parallelizing the search or the lookup in different inverted indexes. Now, if you want to build modern full-text search, a lot of people nowadays are gravitating towards the OpenSearch project. And OpenSearch goes back to decades of production experience with full-text search and other use cases. It's fully open source, hosted under the Linux Foundation, and it's backed by multiple large and medium-sized enterprises, including AWS, as you see here. You can use OpenSearch not only for full-text search, but also for analytics, especially for log and security analytics, and you can use it for modern AI search techniques that we're going to discuss in the rest of this talk. But running OpenSearch in production can be quite a challenge, because OpenSearch is a distributed system. You have to make sure that it's always up and running in production, highly available with all of the backup, software update, etc., all of these processes somehow handled. This is why on AWS, you can also choose to have AWS manage its infrastructure for you using Amazon OpenSearch Service, which is a managed offering of OpenSearch. Going even one step further, if you want to be even more hands-off, you can also take Amazon OpenSearch Serverless, where you basically tell us, I want to have a search workload. I want it to scale from capacity X to capacity Y, and this is it. You can start using it. Now, you also see on this page that both of these options and also the open source project include some integrations into the AI space. OpenSearch itself has some native AI capabilities, but the power also comes from integrating with the rest of ecosystems out there. And this is not only AWS ecosystem, but you can really rely on the technology that you already know and love today. Let's look at some of these AI search cases to see how we can improve the user experience that we discussed before even further. And the first one I want to cover here is semantic search. Semantic search works not by looking at specific words and looking them up in our data set, but looking at the meaning of what a user has put in and searching for similar meanings across the data set. And this is why in our data set we can include something like this cultural tour that you see down here, which is lexically not even related to what the user has put in, but is semantically related, so it's related in meaning. We can also type in something like, I want to take a walk. And in this case, the database is going to return something with walking, but it's also including parks, because I can go to a park to take a walk. Another power of semantic search is that you can use other languages to search for something. So in this case, I typed in the word Geschichte, which is German for history, and I get back results related to history. Now, how semantic search works is by so-called vector embedding models. And vector embedding models are specific AI models that take a given input, in this case a text, and produce a mathematical representation of this input. And as you saw before in the slide, it's a long list of floating point numbers. And it really doesn't mean anything to us humans, but we can now apply mathematical operations to that to make use of it. For instance, we can produce another embedding vector using, for instance, the user query, and produce another one of these list of floating point numbers, which is the vector, and then we can use this to calculate the distance between these different vectors to establish how semantically similar they are. So this is in the end what a semantic search engine will do for you. You may have noticed that in the semantic search case, we're now missing some of the capabilities of the full-text search case that we saw before. For instance, we don't get this highlighting of different words anymore. So in these cases and others, we can leverage hybrid search to make the most out of both of these worlds and combine them together. So you may want to use this for something like, for cases where full-text search doesn't include any results and you at least want to give your user something to work with. You can also use hybrid search to boost the relevancy of the results that are returned by full-text search through semantic similarity. Now, so far, we've stayed basically in the same user experience, right? We provided the user with a text box for input, a search button. Maybe we want to provide them with a bit of a different user experience, where the answer to a question is not a list of results, but a natural language answer produced by a large language model. And this is where retrieval augmented generation, or RAG, come in. Now, as you see here, I asked the search engine in this case, I'm in Chisinau for a conference and would like to see one or two iconic things in the city. What can you recommend? And the system responds with a natural language answer. So how does that work? For the RAG case, what we do first is a semantic search based on the user query. So we do exactly the same as we did in the semantic search case first. So we need, again, some vector search database, like OpenSearch in this case, to give us a list of semantically similar results. But for the RAG case, we don't directly return this result to the user. What we do instead is we feed those results into a large language model and ask the large language model to formulate, based on those items that were returned, formulate a natural language answer. Now, we may want to take this even a step further and not only have a system that retrieves data and gives a natural language answer, but also acts on the user's behalf. So we may want to provide our users with the capability to also book taxis to the attractions that we have stored in our database. And for cases like these, you may want to think about implementing agentic search. For agentic search, we again need to have this semantic search capability. And as you see, we also need some way of booking a taxi in our system. So we may integrate, for instance, with local taxi providers in Chisinau. But in this case, in the agentic search case, we're packaging our capabilities a bit differently. We're packaging the search and the taxi booking each as a so-called tool. And the power of that is that we can then pass a list of those tools to our large language model and have the large language model decide, based on the list of those tools, what would be a good tool to use to fulfill the user request. So what the LLM will first do is it will say, I first need to find a nice museum. And I will use my search tool for that, which seems to provide this capability. It has a defined input, a defined output, so when we get back our results from semantic search, I can continue. I again go to the large language model and tell it, I've searched in my database and I found the following results. What do you want me to do next? And the LLM, and this is especially LLMs that are kind of state-of-the-art or modern LLMs that can do this type of reasoning. The LLM responds to me, well, I also need to book a taxi booking, need to use the taxi booking tool to the address that was returned from my search. So I use the taxi booking tool, I tell the LLM, I've used the taxi booking tool, this is the response. For instance, taxi is coming in 10 minutes. And then, and only then, for the third iteration, will the large language model respond with a natural language answer to my user. Now, as I said before, full-text search is really something that our users are expecting from us nowadays. All of the AI search techniques that I discussed, this cannot be generally said. Maybe in some contexts, in some business domains for certain audiences, people are expecting more and more of these AI capabilities, but it's certainly nothing that is expected across all of these different use cases. And especially, it's not very clear in a particular use case what even is the best user experience to provide to my users. Do they want to have even an agentic capability, or are they happy with just searching for something and having a list of results? And this can be different in different business domains, but it can also be different between now and 3 or 5 years from now. So the question is, how do I decide between these different approaches? And the first thing I would advise for when you go into this AI search space is to very clearly define what you want to achieve with this. I have a lot of customer conversations where the first question is basically, how do I implement semantic search, or how do I do agentic search? And I think this should not be the first question. The first question should be, what do I want to achieve? And this is surprisingly many cases, it may seem obvious, but in many cases is not actually clear. And this is a problem because I've not seen a single customer that started implementing AI search and has ended with the same exact approach that they started with in a production system later on. So you will need this kind of North Star to be able to iterate and to improve your quality over time. When you get started with building, build with evolution in mind. So don't build a system and don't choose a technology stack that limits you to one of these specific approaches. And really, for the search part of your architecture, OpenSearch is a great tool to choose because it can provide all of these different functionalities and features that we discussed, both classic full-text search as well as modern AI search approaches. And last but not least, measure against your business metrics that you set out to improve and iterate over your solution. Now, one last architecture pattern I want to cover in this talk is MCP, or Model Context Protocol. Now, I mainly want to cover this because in some conversations, it seems to me like there's a bit of a misunderstanding how search and MCP work together in practice. And in some conversations, it was even mentioned that maybe MCP replaces the need to do a proper search. Now, I don't really think that's the case. MCP can really help you if you decide to build some agentic capabilities into your product, but you don't necessarily want to build the user interface for that. So it may be that your users would love to have some agentic capabilities, but they also love their, for instance, Anthropic Claude desktop application, where they are using all these AI agent features currently. And MCP can help you establish that and make that work. To implement this, firstly, what we need to do, we still have this search tool and a taxi booking tool. But in this case, we're packaging both of these tools as a so-called MCP server. And the benefit of that is that MCP servers can be easily integrated and connected to from so-called MCP clients. And MCP clients, there are many out there. So you see here Anthropic Claude Code, the desktop application. OpenAI supports it, AWS's own QDeveloper, and many, many more of these different existing AI agent interfaces out there. So with all this said, I was not really able to cover all of the different AI search techniques out there. And I really encourage you to explore this a bit more. We've set up a great demo on Hugging Face in this first QR code here that you can go, check out, and just try out these different capabilities on your own smartphone. It's an e-commerce shop, and it takes you through these different search techniques, and you can just try them out one by one and maybe be inspired by what you can build in your own search experience. There's also a recently released MCP reference architecture, which covers how to securely build these MCP servers on top of AWS. I'd also like to encourage you to attend a workshop tomorrow that I'll be hosting, where I'll go a bit more hands-on on how to implement these things. So we'll have an AWS account ready for you, and you'll go and implement some of these AI search capabilities there yourself. So with that, I want to thank you for being here. Thank you for listening. I'm looking forward to great conversations to be had at this conference and beyond. Feel free to connect on LinkedIn or just shoot over an email. I'm happy to engage with your specific search use case. So let's build the search of the future together. Thank you very much.